This talk is about how we use the transmission electron microscopy method to study the electrode materials and their electrochemical reactions at a nanoscale. So we know battery is important to our lives. Here we show a few of the examples like our remote control, our watch, and our cell phone, laptop. For some of them, we can only use them once. They cannot be rechargeable, so we call them primary batteries. For some of others, we can recharge them after a one-time use. So apparently, this rechargeable battery is more interesting. So lithium-ion battery is a kind of a rechargeable battery. Here's the image of the first lithium-ion battery, which was commercialized by Sony in 1991. And because lithium is the lightest metal and it has the greatest electrical potentials with the materials, so this gives a big advantage. Compared with other batteries, it has the highest energy density. Here, the x-axis is the energy density per weight, and the y-axis is the energy density per volume. We can see in both terms, lithium-ion battery is much better than other kind of batteries. In addition, the lithium-ion battery is a very low maintenance. It also has a very low self-discharge current. So those make it a huge success in portable devices. Let's show in here. For the portable devices like our cell phone or computers, the voltage of a battery is about several watts or tens of watts. For a larger application, then we need to integrate thousands of batteries together. For example, for a car used for Tesla, we have to integrate 7,100 batteries together, which give us a 300 kilowatts power. It can make our car run more than 200 miles. But the cost is here, about $12,000. It's quite expensive. The battery has been widely used in our life, but we are not satisfied. This is because we have to charge our cell phone every day, and otherwise we are not able to communicate with our friends. For the car, it only runs 200 miles, but for a gasoline engine car, it can run easily more than 400 miles. So we want a battery in future. For the future battery, we want a battery that has more energy, then it requires a higher capacity and power. We want the battery can run a longer life, which means we have a better cycling stability. We want the battery can be charged faster, which requires us to improve the rate capability. We want the battery can be cheaper, which used for larger scale applications, like a stationary battery. At the end, we want the battery is environmental friendly when we manufacture battery and dispose them. So here is the structure of a lithium battery. It has many components here. Even more complicated for the electrode, it is a mixture of different compounds. So the battery is a complicated system. We can optimize the performance of each component or redesign the battery. That is an engineering approach. The industry using engineering approach can increase 5% performance every year. This is very good, but not good enough. So we can also invent some new materials to be the electrode, or invent a completely new chemistry for the battery. That's a kind of a scientific approach. If we have the better battery materials, the performance will be dramatically improved. So for doing that, we need to deeply understand what happened in those new electrode materials. That's what I'm going to talk about in this presentation. So here is the outline. First, I will introduce the background knowledge of a lithium-ion battery, and I will also introduce the main approach we are going to use in our work, transmission electron microscopy. In the science part, I will give two cases. The first case is of iron oxyfluoride cathode materials. I will talk about how the cold shell nanostructure affects its cycling stability. In the second case of nickel oxide anode material, I will talk about how the reaction pathway affects its rate performance. The last part is summary and outlook. So here is a schematic structure of a lithium-ion battery. From the scientific view, it has mainly three components. Here, the anode, which is a negative electrode. Here is the cathode, which is a positive electrode. Here is the electrolyte. For our current battery, we use the graphite as the anode material. We use the lithium cobalt oxide as the cathode materials. In both materials, there are spaces in the materials where the lithium can go in and go out. And the electrolyte is normally the lithium salt soluted in organic solvent. The function of electrolyte is to make the lithium ion transfer through, but blocking the transfer of electron. During we use the battery, we call it discharging. The lithium ion will come out of the anode, go through the electrolyte, and insert in cathode. At the same time, because the electron cannot go through the electrolyte, it will go through the outside circuit, then react with lithium ions at the cathode part. When we do the charging, the whole process will be reversed. So now talk about why lithium-ion battery can store energy. This is because the lithium ion have different electrochemical potentials at the anode and the cathode. During the discharging, the lithium ion going from the anode to cathode, then it will release energy, transfer the electrochemical energy to electricity. This is very similar to here. If we put some water on the top, when the water coming down here, it will pump some station, transfer this potential energy to the electricity. When we discharge it, we can pump the water out. So this approach, we call it a pumped hydroelectric storage station. So we also use it to store energy at a large scale. So there are two parameters decided how much energy a battery can store. The first thing is capacity, which means how much lithium ions the anode and the cathode can contain. It's like how big the pool is. Another parameter is the voltage, which is the potential difference between the anode and the cathode. And that is like how high this hill is. So here we list some typical electrode materials. The x-axis is the capacity. The y-axis is the voltage. The cathode materials are represented in blue, and the anode materials are represented in white. We can see the graphite is sitting here, and the lithium cobalt oxide is sitting here. Their capacity is not high. So for the new materials, one task is to looking for the materials has a high capacity. Most of current electrode materials are intercalation materials. As I mentioned, there are space inside this structure. The lithium ion can go in during the discharge and come out during the charge. But there is another kind of electrode materials. It's conversion materials. It's showing here. This is the general reaction formula of conversion materials. It's a 3D compound. It reacts with lithium and becomes lithium compound and a 3D metal. 3D metal. So this is a redox reaction. The redox reaction means there is a charge transfer during this reaction. So from left to right is discharge process, and from right to left is a charge process in our case. So this compared to insertion or intercalation materials, and this one has a much These type of materials have much higher capacity, but on the other hand, the cycling stability is not high. It means after several cycles, after a number of cycles, the battery will fail, compared with our current used battery, which can last several thousand times. People have found the cycling problem of convergent materials can be partially improved using nanomaterials. Here is an example of iron oxide. So the x-axis is the concentration of lithium, and the y-axis is the voltage. The blue represents the materials with the nano-sized particles. And here, the red one is the curve of micron-sized particles. These are the cycling curve. One cycle means one discharge and charge process. So here, the x value of this curve corresponding to the capacity left. We can see for micron-sized particles, after only 10 times, the capacity is only 10% of original one. But for the nano-sized particles, after 38 cycles, the capacity is still about 40%. So what happened here? Why, when with the size of the materials goes from micron to nano, the cycling stability will improve because there are space between the nanoparticles, which space can accumulate the volume expansion, which I forgot to mention. The volume expansion is the main problem of the cycling stability. On the other hand, when the size goes from micron to nano, then the surface area will increase, and the diffusion distance of lithium will be shortened. In that case, the reaction can happen faster. Then it will increase the rate capability we will introduce later. Here we know the reaction happened at a nanoscale, but the performance we are measuring is happening at the cell scale. To link them together, we need the experimental tools to cover the whole range. Here, we take advantage of the high resolution of electron microscopy and the larger field of view of a synchrotron X-ray to study the materials change. Now we are going to talk about the transmission electron microscopy. So TEM group is one of the scientific groups in CFN. We have 6 permanent staff here, and the group leader is Eric Stark. And we have currently have 4 state-of-art microscopes here. Among them, the Hitachi 2700 and the FEI microscope are equipped with aberration corrector, which gives them a best spatial resolution at 0.8 angstrom. So here is a model of a transmission electron microscope, or TEM. It has a very similar structure of an optical microscope. Here is an electron source which produces the electron. Then the electron are accelerated to several 100,000 electron volts. We have the lens system to focus the electron. Then the electron penetrate through the specimen and be detected here with use a detector. The beauty of this technique is it can integrate different functions such as diffraction, imaging, and spectroscopy into one station. It's a single station with the multi-functions of many beamlines can use to solve your problem. So here I want to introduce a very important spectroscopy technique, electron energy loss spectroscopy, or ELS. We have the high electron penetrate through the sample. It will interact with materials inelastically, then lose energy. So when it interacts with co-electrons, it will give co-loss ELS. When it interacts with valence electrons, it will give a valence ELS. From the valence use, we can know how thick is the sample and the dielectric function of the sample. From the core loss use here, we can get the chemical information of the sample materials. So the chemical information means not only tell us what kind of element they are, but also their valence and the bonding information. There is another kind of working mode of TEM, scanning transmission electron microscopy, or STEM. This structure of STEM, it's very similar to TEM, but instead of a parallel beam on the sample, here we focus the electron beam to very small probe and scanning this probe on the sample. So the working function is very similar to scanning tunneling microscopy, or STM. But from STM, what we got is the information of the surface of the sample. Here, what we got is the projection of a 3D matter. So used here as a hollow annular dark field detector, we can take high-angle annular dark field image. Here is a hard-diff image of a nanoparticle. Remember, here what we got is the 2D projection of a 3D image. Here, each one bright spot corresponding to the atomic columns. One advantage of a hard-diff image is it is a contrast here proportional to the atomic number Z. So this is a Z contrast imaging. It gives us a big convenience to interpret our image. At the same time, we can have a detector here to detect the transmitted electron. We can take the use spectrum. By combining these two techniques together, we can simultaneously take image and take the spectrum at each point, which gives us a spectrum imaging. It means in this imaging, at every pixel, we can know not only where are the atoms, but what are they. So here I want to introduce the correction of aberration. What is spherical aberration is showing here. For a perfect length system, the beam will focus at one point. But if the length system is not perfect, it will become blurry here, then reduce the resolution. Similar aberration happened in Hubble Space Telescope. Here's the image of a galaxy before the aberration created. Here is after it created. So we can see a huge improvement. People in transmission electron microscopy field invent a similar technique. Here is an example of a silicon 110 particle. So this is we switch off the stem. This we switch on the this we switch off the character. This we switch on the character. From the character one, we can clearly see the silicon 110 dumbbell, which corresponding to 0.134 nanometer. And actually, as we know, this is a projection of this 3D crystal structure. Here is a picture of the aberration crater we used for Hitachi microscope. These are kind of magnetic coils together. We use the computer to control the current here, then to compensate the problem in the length system. So even we have advanced microscope with 0.8 angstrom, it not means we are able to always get the resolution. Another big challenge is the beam effect. This is because the interaction between the electron and the materials is 10,000 times higher than the X-ray. So as a negative consequence, it will give much more severe beam effect. Here is an example of a lithium titanium oxide spin-out sample. This is an ADF image. But if we scan the beam here, we see the crystal structure has been changed. This is an enlarged picture of this one. So this, as we thought, this is a ADF image. So each bright point corresponding to a column of atoms, the arrangement has been changed. So we see this pattern. Here is a control experiment to identify the beam effect. These are the one nanoparticle we scanning on it for 20 minutes. This is the image before the irradiation. This is the diffraction before the irradiation. After 20 minutes, we see the structure has been changed. Combined with other results, we identify what happens if the crystal structure change from spinel to rock salt. And what happened if the electron beam will break the lithium and the oxygen bond and sputter the oxygen out of the sample, then the whole structure collapses and reconstruct to a more compact structure. So based on our experience and other experimental results, we can have the general picture of electron beam effect. The x-axis is the total dose, which means how many electrons has been through the sample. The y-axis is the dose rate, which is the electron beam intensity. Here we show we have to control the value of both of them to get the damage negligible zone. So the take-home message here is for doing electrode materials for lithium-ion battery, we need to do the electron beam test. We need to know where is the limitation of the dose and the dose rate we use to control the damage effect can be acceptable. Our research goal is to understand how the structural change in electron materials links to the performance. So what we can do is here, we can control the charging process of a battery cell here. We can control the current and the charging time to a certain state of charge. Then we take this sample, put it into TM, and look at it. Here is an example of a half-discharged nickel oxide nanoplate. And this is an ADF image, so the bright part corresponds to sample, and the dark region is a hole, is empty here. So the scale bar here is 10 nanometer. The nanoparticles we see here are actually a nickel nanoparticle that's reduced from nickel oxide. This part is unreacted nickel oxide. So the requirement of this reaction happen is we have both lithium ions and electrons go to the interface, then make a redox reaction happen there. So from this image, we can deduce the lithium ions is coming from this way, the electrons coming from this way. They met here. So this is an example. In our work, to make things easier, we are always using a half battery, which means we use the lithium anode, lithium metal as anode, and use the active materials as cathode. In that case, the discharging process is the process of insertion of lithium, so we call it lithiization. And reversely, the charge process is when the lithium get out of the structure, we call it delithiization. Now look at our first case. The first case is on iron oxide fluoride cathode. Most convergent materials are anode materials, but iron fluoride has a high voltage with lithium, so it is a rare cathode materials. The problem of these materials is showing here. This is a cycling date. The x-axis is the numbers of discharge and charge. The y-axis is the capacity. We can see only after 30 cycles, the capacity of iron fluoride decreases a lot. People have found if we partially use oxygen to replace the fluorine in the structure, even the crystal structure does not change. The cycling stability is largely improved. We want to understand why here. The conversion reaction happened in this material is showing here. The original materials is a rutile type structure. When we discharge it, it becomes an ordered phase here. When we further discharge it, then these materials will decompose to a mixture of lithium fluoride, BCC iron, and rock cell type lithium iron fluoride structure. People have done synchrotron X-ray on these materials. The axis is the concentration of lithium. The first half part is the discharge process, and the second half part is the charge process. So first we see the black curve here. This is a discharge and charge curve. The voltage is showing on the right. We have found 4 different phases here, besides the lithium fluoride phase. The 4 phases we found here is rutile phase, rock cell phase, and BCC iron phase, and nano-rutile phase. We can see here from the first discharge, the materials becomes a mixture of rock salt and BCC iron. After the charge, the rock salt phase does not change, but the BCC iron phase becomes a nano-rutile phase. I mean, the materials after one cycle has been changed. It's not the same to the original materials anymore. We want to understand why it's like that. In addition, we still don't understand how this structural change affects its improved cycling stability. So we're able to take high-resolution STEM EUs from this sample. These are the spectrum imaging mapping, where the red one represents the concentration of fluorine. The green one represents the concentration of oxygen. We have done this not only from one particular particle. We've done it for many areas. That's to ensure what we see is a general phenomenon. It's not only one single case. So at the pristine sample, we see an oxygen-rich shell and a fluorine-rich core. And we see after discharge and charge, this shell is very stable. The thickness, here's the scale bars are 5 nanometer. So the thickness of the shell is about 1.2 to 2.2 nanometer. Here, this is strange. We want to understand why, and we also want to see how the reaction happened at the core and the shell. We can measure the local valence of iron from their EUS spectrum. Here, what we do is we integrate the EUS spectrum at the core and the shell and put them together here. So the red curves are from the shell, and the black curves are from the core. We can see the peaks of fluorine KH and iron L edges. From the ratio of L3-L2 ratio of iron, we can quantify the valence of iron before and after lithiization. Here is the result. At the core, in red, we can see the valence does not change much, but at the shell. But at the core area, we can see after lithiization, the iron is reduced. After delithiization, it was oxide again. Here, what we see is the valence of the shell is stable. The redox reaction mainly happened at the core area. We want to know the details, so we have done a high-resolution STEM imaging. This is a sample after lithiization. We can see it was one particle at the pristine materials. Then it breaks to 5 nanoparticles, showing here. We can see the 5 nanoparticles both at the shell and the core area. The scale bar is 2 nanometer. So the size of the 5 nanoparticles is about 2 nanometer. And we can do a fast Fourier transform from each particles, showing here. The result of a fast Fourier transform is similar to diffraction pattern can be used for phase identification. They looked very similar, but if we measure them carefully, we can measure the lattice disk constant of the shell particle is a little bit larger than the particle in the shell. Combined with use result, we identify the shell particles are lithium iron fluoride, lithium iron oxide rock cell structure, and the nanoparticles at the shell is the BCC ion. Interestingly, they have very similar lattice constant, and that makes them can reduce the misfit strain between them when the reaction happened. So combined above result, here we can summarize the microscopic reaction pattern. In the shell, in the pristine materials is oxygen-rich rutile structure. After first discharge, it becomes oxygen-rich rock cell structure. After charge, this structure does not change. In the coal, it was fluorine-rich rutile structure in the coal. After discharge, it decomposed into a mixture of iron and lithium fluoride. After the charge, it is oxidized back to nano-sized rutile structure. This result is consistent with synchrotron S3 result. But what we know here is the redox reaction mainly happened at a coal area, and the shell area is very stable during the further charge and discharge. So why the iron oxyfluoride has a better cycling stability? Because the shell is stable during the reaction. It can confine the reaction within one particles to make this reaction reversible. Now we are going to talking about the second case of nickel oxide anode materials. In this work, we combine the ex situ and the in situ TM together. For the ex situ, we have mentioned it's easy. We can put a TM grid into the cell and cycling it to the certain state of charge, then take the grid out, look at it under TM. For the in situ work, we have been using a nanofactory STM holder. Here, we can put a piece of lithium metal on the tip of STM. We use that as anode. Then we use inorganic lithium oxide as cathode. We put active materials in a half TM grid as cathode materials. So here we can apply a bias under the TM and to look at the electrochemical reaction in real time. So in last case, we have known in the last case of iron oxyfluoride, we have known the nanostructure and the local chemistry will affect the cycling performance. On the other hand, here we see the migration of lithium ions during the reaction will also have important effect on the performance. Here is a cartoon showing the process. The blue one is showing the unreacted sample, and the red one is reacted sample. From the unreacted pristine sample to full elucidated sample, there could be different reaction pathways. For example, here, the lithium can go into the structure homogeneously, which have a solid solution process. In this one, the lithium can go from one side to the other side. In this one, the lithium can go from the edge to the center. In this case, the lithium can go to its own route through the particle. So because of the local reaction condition for the electromaterials are different, so this different reaction route may affect the reaction speed of these materials, which affect the overall performance. The sample we are looking at is a nickel oxide nanoplate. These are ADF images at a different magnification. The bright part are the active materials, and here we know the black part are the hole. So it is 1-1-1 oriented, and the thickness of this sample is about 10 nanometer. This is a perfect example for TM study because it's very thin and the green is very large. It allows us to study the intrinsic reaction mechanism. Here is the reaction formula. The nickel oxide will be reduced by lithium to form the nickel metallic nickel and lithium oxide. During the reaction, the volume will have a 120% expansion. We want to study the rate capability of this sample. Here is the true charge-discharge curve at a different rate. The x-axis is the capacity. The y-axis is the voltage. So we discharge and charge this sample at 2 different rates. Here is 0.1 C, means we discharge it for 10 hours. The red one is at 10 C, which means we only discharge it for 6 minutes, but with 100 times larger current. We keep the same how many electrons we put in this system. Here we can see at high rate, the capacity is much lower than in the low rate. This is a general phenomenon we see in any electron materials. We call it a rate capability. And this is easy to understand because if we charge our battery with a lower current and a longer time, we can store more energy. The interesting part is also here, both values at high rate and low rate are higher than the theoretical value. This means during the first discharge, there are a lot of side reaction happened. The side reaction happened is between the active materials and the electrolyte. So to measure how much nickel 2+ has been reduced, we have been used synchrotron X-ray absorption at light source 1. The black one is the result at a low rate. We can see a linear change with the state of charge. But at the red one, here the x-axis is the state of charge, and the y-axis is how much is the portion of the reduction of nickel oxide. For the red one, we charge it at a high rate. We can see a delayed beginning. At the end, we also can find there are some materials is not reacted. We suspend that not reacted materials might be the reason of this capacity reduction. We will prove it later. We have done an SUTM study on these materials. These are some examples of half-reacted. So we have observed 3 kinds of morphologies. Those are ADF image, so the bright part corresponding to the nickel oxide and the dark part corresponding to the hole. And the nanoparticles here we see are nickel nanoparticles. It's kind of a fingerprint of the reaction. From the left one, we see the reaction happened from the left to right. It's a kind of reaction interior to interior. We call it a bulk reaction mode. For those two, we see the reactions also coming from the near surface to interior. Remember what we have here is a 2D projection of a 3D image. So actually the nanoparticles we see here is from above and the bottom of the sample. This one, the reaction happened homogeneously from outside to inside. We call it a near surface mode. In this one, it's very interesting because we see the reaction fingers coming from the outside to inside. That one have not been observed in other materials. So we did a further analytical TEM. On the left one is the STEM use result. This is an ADF image. We can see reaction fingers here. This one is a use mapping of this area. The red one, the red color represents the concentration of lithium. We can see there are lithium-rich area. If we do use line scan crossing the reaction fingers, we can measure the nickel LH. Then we can quantify the valence of the nickel. We see indeed at the finger area the nickel is reduced. So here we prove this one is really the reaction area. It's not a crack due to the strain. We can also take a 3D electron tomography. For normally TM image is a 2D projection, but if we tilt the sample to many degrees and collect those TM image, reconstruct them with computer, we are able to get a 3D structure of the materials. This we can see here are the reaction fingers. From the 3D tomography, we know the reaction fingers is really have been through the sample. It's not only a reaction happened on the surface. To understand how the reaction happened at a different rate, we have done a statistical analysis on TM samples at a different state of charge at a different rate. It means we take samples from each state of charge and at a different rate. It's just a lot of work to do. And this costs Kai and I a lot of efforts. This on the left, what we show is the bulk mode we found in the materials. We think the bulk mode is an immediate consequence of finger mode. On the right is what we see from the surface mode. So we can do a statistical analysis on how many events in different samples. Here's the result. What we can see is at a high discharging rate, the x-axis is the state of charge. The y-axis is the ratio between surface mode and the bulk mode. Here what we see is at a high discharging rate, the surface mode dominates the reaction. This curve is similar to what we have been seeing from the synchrotron X-ray. But remember here, there are two different things. In the TEM, what we see is a difference of reaction mode. But for the synchrotron, what we measured here is the reaction speed. So is there any correlation between them? We need to answer it using the in situ electron microscopy. First, we did an in situ diffraction experiment. So we can we see the change of the spots, which corresponds to the crystal structure change during the in situ reaction. So we plot the patterns at here with time sequence. Compared to the reference, we identify in the in situ cell, the phase reaction is identical to what happened in real cell. This is important because at an in situ cell, the electrochemical condition is different. We have to identify what we see is not artifacts. So we can do the in situ imaging. On the left is it is on TM mode. So the dark part are the sample. So let's see the video. And we will see here the reaction happened from the surface to inside. And the darker nanoparticles are nickel nanoparticle. And it forms a composite structure with lithium oxide. So this video showing us how the near surface mode formed. Now let's see the radio on right. So this is on at the dark field mode, where the bright part are the sample and the dark part are the hole. In this video, we see not only the surface mode happen here, also the formation of the reaction fingers. So here is the time sequence image of those two videos. From this image, we can measure the movement of a reaction interface, then quantify the reaction speed in these two reaction modes. Here's the result. We can see the reaction speed of the finger mode is 10 times faster than the surface mode. So here, by the in situ imaging video, we really correlate the reaction mode and the reaction speed. In addition, we found an incubation time. That time is after the surface wetting and before the reaction fingers can nucleate. In our whole videos, that time is about 100 seconds. So combine the all ex situ, in situ, and synchrotron result, we are able to get the reaction picture of this sample. So before, when the lithium ion reach on the surface, before the fingers can nucleate, there is a 100-second incubation time. Then otherwise, there are going to be heterogeneous reaction mode. One mode is the finger mode, it's faster. The other is the shrinking cone mode or near surface mode, which is slower. Why in the high-speed charging, the capacity is lower? So there are two reasons. First, this 100-second incubation time take a lot of portion of the charging, so which delay the reaction. And the second, the high discharging rate will promote the happening of shrinking cone mode, which further delayed the electrochemical reaction. So after we got the picture, there are still some questions we cannot answer with experimental data. For example, why there are reaction fingers? Our collaborators from MIT have done the strain analysis. Here, when the reaction happened at the finger, at the tip of the finger, it is under the tensile strain. And the edge of the finger, it under the compressive strain. The tensile strain will fast the lithium the reaction, while at under the compressive stress, the reaction will be slower. So this is how the reaction happened. In this case, we can see the reaction pathway coupled with the local strain can largely affect the performance at a different rate. This conclusion could be applied to any kind of reaction where there are volume expansion, any kind of lithium battery reaction. So, as a summary, I hope I'm able to convince you that analytical TM technique can help you to study the local phase, chemistry, and valence. At the same time, in situ TM may help to probe the dynamical process of the reaction in nanoscale. And there are some outlooks. We know the lithium-ion battery is very important, but there are some new ideas about the future battery system, like a sodium-ion battery, lithium-sulfur battery, and a magnesium-ion battery. The good thing is in Brookhaven, we have already a bunch of groups are working on those new ideas. On the other hand, what we are doing is the fundamental research, but these techniques can be used to solve the practical issues, such as capacity feeding and safety, and people can also put efforts to explore some new electrode materials. here I want to acknowledge the people who contributed to this talk. I want to thank the people who helped me on TM work to prepare the electrode materials and make the battery tests. I want to thank the collaborators for the theoretical work and the technical help. So here, the last image, I want to show the people, our team in Brookhaven. So thank you for your attention. Yeah, actually, we can see the lithium-ion battery is quite a new area. The first commercial one is in 1991. So generally, people don't have knowledge on, I mean, people have been used certain of materials for lithium-ion battery. Now people are exploring more possibility in more materials. The materials I was talking about, the conversion materials, this is one example. This kind of materials already been synthesized for other purpose. Now people to explore the possibility of them to be used in lithium-ion battery materials. So people have different ways to synthesize them. They can do the traditional solid-state reaction to make it formed, because that's mainly oxides. It's quite easy. People can use some chemical method to make them. And people even can buy them from some company. Yeah, but it's very important to optimize the synthesis. As I show, there are some guy in Brookhaven working on that. Yeah, please.
What are the characteristics of the charge and discharge? In some cases, you have large crystal.
Oh, you mean the hysteresis? Oh, yeah. The hysteresis is important issue. Sorry, I forgot to mention. It's mainly coming from the volume expansion of the conversion materials. So, but how large it is that is depend on the rate we use to charge. We call it polarization. It's not useful. We want to reduce it. Yes, but yeah, actually that kind of hysteresis is a problem because it means we lost energy during the charging. So the problem is the energy will tend to be heat. So that's a problem, actually, very important issue. People try to make the discharge and charge curve close. That means there are less internal, energy waste.
Yeah, I just got a question on your material is fairly polycrystalline.
Yeah, this sample have a very large green. We know where are the green boundaries. In the beginning, we thought maybe they preferred at a green boundary, but in reality, it's not always. Actually, because where there are I think in the beginning it's like a nucleation process. When somewhere the reaction speed is faster, then it go more into the sample. Then this difference will be enlarged due to the strain. So it actually happened in both boundary and other part.
So my question was very
I believe our reaction is not a diffusion controlled process. That can be evidenced by several things. First, we see the reaction fingers happened at the same part, where very close part, the near surface mode happened. So it is not controlled by how much lithium ions get to there. Actually, the reaction speed in principle depends on several things. First is the local potential. The second is the local gradient. The third is the strain. We are trying to use the phase field theory to address what is the main reactor, but I think it's very complicated in reality. Actually, here I want to mention in the real battery, the reaction is not happened immediately everywhere. It's not homogeneous, it's inhomogeneous.